Okay, so what we're doing today, Year 11, is we're looking at absolute value functions. Now, we looked at absolute value functions back in equations, and we looked at how we can solve those equations with absolute value functions, as well as what they are. So an absolute value function is the magnitude or distance of the number from 0 on a number line, so that its value is always positive or 0. We also know that the absolute value of x is also equal to the square root of x squared. So we can graph these absolute value functions, which is what we are doing today, where we have y equals the absolute value of x. Now we can do this by completing a table of values. So if we were to find the absolute value of -3, we would get +3. The absolute value of -2 is +2. The absolute value of -1 is 1, absolute value of 0 is 0, absolute value of 1 is 1, absolute value of 2 is 2, and absolute value of 3 is 3. So we can plot these points on our number line, and when we do so, we see that our graph for an absolute value function is a V. So it's two straight line portions of our graph, and we have a V shape for our absolute value function. Okay. So, like I said, the graph of our y equals absolute value of x is V-shaped. Okay, and it consists of two lines. What we have is, I didn't answer our domain of this value, but the domain is all the values of x it can be. Okay, so our domain is going to be -infinity to infinity, and then our range is all of our y values. So our y values is 0 to infinity, and we do our square bracket because it includes 0. Now, like I said, the graph of y equals the absolute value of x is V-shaped, and it consists of two lines. So we have line 1 is there, and line 2 is here, okay? And the two lines meet at that point. They have the gradients of -1 and 1, okay? And they meet at that point 0, 0. Our absolute value function is symmetrical about the y-axis. So if it's symmetrical about the y-axis as a function, it means that it's an even function. Okay, we're just going to rewrite down that domain. So our domain is -infinity to infinity, which we can also write as all real. Okay, or we also have our range is 0 to infinity. We can also write that as y is greater than or equal to 0. Both ways I've written the domain there are accurate, and we can do that. Now, we can write our absolute value function as a piecewise function. So yesterday we looked at piecewise functions if you were absent, and you need to catch that up. So with a piecewise function, we have our two pieces or more. And what we have for the absolute value of x is we have x if x is greater than 0. So that is this portion of our graph here. And then we have -x if x is less than 0, which is this portion of our graph there. Okay, so we can always break our graph up into our two pieces for our absolute value function to get our piecewise function. Okay, we also have the absolute value of fx is equal to fx if x is greater than 0 and -fx if x is less than 0. What we're going to do is look at our first example. So our first example is to sketch fx equals the absolute value of x minus 1, and we're going to state its domain and range. The first thing that we're going to do is we're going to look at our absolute value function that we just drew. What we have when we minus 1 from that function is we have that fx equals the absolute value of x minus 1 is our parent function y equals the absolute value of x, or fx equals the absolute value of x, and it is just translated 1 unit down. Okay, so that means we have our graph 1 unit down. So if we were to look at our absolute value function and we were to just shift that 1 unit down, we would have that the point that it meets is at -1 on our y-axis. And then we are just drawing our lines y equals x and y equals negative x from that point. Okay, so we're just shifting that v down by 1. Does that make sense? Okay, so that is our function f(x) equals the absolute value of x minus 1. So we can do it that way. Okay, so that's way 1 of sketching our absolute value functions. Our other way is to look at our piecewise function. So f(x) equals, we have our positive version of x minus 1, and that is for x is greater than or equal to 0. Or we have our negative x minus 1 for x is less than 0. Okay, so the top part here is my right-hand side of my y-axis, and the bottom part here is my left-hand side of my y-axis. Does that make sense? So we should all know how to sketch x minus 1. X minus 1 is got a y-intercept of -1 and a gradient of 1. So we start at -1 and we work our way up, and then the same with the other version, negative x minus 1. Okay, the second part of this question, so we've sketched it, and I've talked about the 2 different ways we can sketch it. The second bit is our domain. So our domain of any absolute value function is always going to be -infinity to infinity. Our range, however, is what our y values are. So where is our minimum y value here? Yeah, -1, and it goes all the way up to infinity because we have our arrows, meaning that it just keeps on going. Once you've copied that down, turn the page for me and we'll look at example 2. So example 2, we want to now sketch the graph of y equals the absolute value of x plus 2. So what we have with this is we have that our plus 2 is now inside our absolute value function. So what we have is that y equals the absolute value of x plus 2 is our parent function. Y equals the absolute value of x that has been translated 2 units left. Okay, so when we have a plus 2, it means it's being translated 2 units to the left. Okay, now that's a little bit confusing. Well, it is a bit confusing. It's not a bit confusing. How I worked out if it's 2 units left is we can work out our piecewise function. So with our piecewise function, we'll have y equals the bracket of x plus 2. That's our positive version. And what we do to work out what it's for is we use our function x plus 2, because x plus 2 is all inside our absolute value, is greater than or equal to 0. And then we have our negative version. So we will have our negative lots of x plus 2 for x plus 2 is less than 0, is how we write it as a piecewise function. Okay, we can tidy this up so we get y equals our piecewise function of x plus 2 and minus x minus 2. Okay, and they are both for x is greater than minus 2 okay, because we are solving our inequality to make x the subject. So what this means is we are just going to then sketch, so we'd be asked to sketch y equals x plus 2 for x is greater than or equal to minus 2. Okay, x plus 2 has a y-intercept equals 2, and it has a gradient equals 1. So if I was to sketch my y equals x plus 2, I would start at my y-intercept of 2, and I rise 1, run 1, rise 1, run 1 to get my gradient. But I need to go all the way to where my x equals minus 2 is. Okay, so I need to go all the way down to where minus 2 is. It just happens that that is our x-intercept on here. Okay, that's our first portion of our graph. Then we would sketch y equals negative x minus 2 for x is less than negative 2. Okay, so that means we have a gradient equals negative 1, and our y-intercept is negative 2. So if I put a dot at my y-intercept of negative 2, it's not going to exist because I only want my values where x is less than negative 2. But I can just put imaginary dots there until I get to where x is less than negative 2. And then these dots are where it really starts to count and are the ones that are part of my function. So we only want it, that part of our function, where x is less than negative 2. So only from here across. Does that make sense? So the light blue dots that I did here and here, they don't exist. So I wouldn't be doing them. I'd just be going, okay, so I start there, dot, dot, keep going to get where my line is. Does that make sense to everyone? Now, this question doesn't ask us for our domain and range, okay, but our domain would be negative, and I'm going to just write it down anyway underneath. Our domain is going to be negative infinity to infinity, and our range is just 0 to infinity. Okay, so when we are shifted to the left or the right of our absolute value function, it doesn't change our domain or range. Now, also remember I said that the graph y equals the absolute value of x plus 2 was just our parent function translated 2 units to the right. Because if I was to really quickly, you don't need to do this, but if I was to draw in my parent function, do you see how it's just been moved 2 units to the right? Yes, cool. Now it's 2 units to the right because our x-intercept is minus 2 if we let y equal 0. Okay, so whatever the, if it's moving to left or right, it's the opposite sign inside our absolute value. Okay, the last thing that we're going to do is we're going to look at equation solving absolute values. So we can solve absolute value equations algebraically. We learned how to do that back in topic 2, but we can also sketch the absolute value function and a horizontal line to find the points of intersection. Now, what we want to do is we want to sketch 2 lines. We need to sketch our function y equals the absolute value of 2x minus 1 and y equals 3. Which one is the easiest one to sketch there? Y equals 3. So that's what I'm going to do first. There's no point mucking around with it. Y equals 3 is our horizontal line going through y equals 3. Arrow, arrow, right, that it's y equals 3. Okay. Now, with our y equals the absolute value of 2x minus 1, we're going to look at it in the piecewise value, okay? Because we haven't just translated it horizontally. We have a lot more going on inside that absolute value symbol. So what we'll have is we'll have y equals our piecewise function of 2x minus 1 for 2x minus 1 is greater than or equal to 0, and minus lots of 2x minus 1 for 2x minus 1 is less than 0. Okay, so what this will be is y equals our piecewise function of 2x minus 1 and negative 2x plus 1. Now, how we work out what it's for is we have to make x the subject. So if we make x the subject for our inequalities, we'll have 2x is greater than or equal to 1 and x is greater than or equal to a half. Okay, it's going to be the same for both of them. We're just solving to make x the subject. So it'll be x is greater than or equal to a half, and it will also be for x is less than a half. Does anyone have any questions about that? Okay, so what we're going to do is we need to sketch both pieces of our piecewise function now. So we're going to sketch y equals 2x minus 1 for x is greater than or equal to a half. Okay, so what we have is our 2 tells us that we have a gradient equals 2. Our minus 1 is our y-intercept equals minus 1. All right, so at our a half, x equals a half, that yellow line is where we're drawing our function from on the right-hand side of that yellow line. Does that make sense? Okay, we're going to have some bits that we don't want though. So we don't want our y-intercept at negative 1 because that's on the left-hand side of our yellow line. But we can put a very light dot there, okay, to know that that is like a part of the function if we had the whole thing. Okay, then our next one to easily draw the linear line is we go up 2 across 1 for our gradient. Remember, gradient is rise over run. So we go up 2 across 1, up 2 across 1, up 2 across 1. So these dots here are my key points on my graph, and I'm going to line up my ruler so that it's still touching where my minus 1 intercept is, but I'm going to draw my line so that it stops where x equals a half is. Does that make sense? Yep. Then, now that we've sketched that side, we then want to sketch our left-hand side. To be honest, it doesn't matter which order that you sketch these in, but I'm now going to sketch y equals negative 2x minus 1 for x is less than a half. Okay, so this time I have my gradient is negative 2. And my y-intercept, oh, it's a plus 1. I've written that down wrong. My y-intercept is positive 1. So when I put my dot at my y-intercept, it actually exists where x is less than a half. So I can put a proper dot there. And then when we're doing our negative gradient, we can still rise up 2, but we go 1 across to the left. Okay, we rise up 2, we go 1 across to the left this time because a negative gradient is going from the top down, going left to right. Okay, if I was to drop 2 and go to the right, I would have a dot there at 1 minus 1, and that dot is on the wrong side of my line where x equals a half is. Okay, then we just put a dot a line like so. Now this one was a little bit trickier to graph, would we agree? Yeah? Okay, what do we notice about both sides that we have graphed? They're symmetrical. Okay, so really we just need to sketch our positive side because that's normally the easier side to sketch, and then we can just line up our dots. Okay, so I know you've already done all this. I'm just going to show you what I mean. So what we have is we had a dot here at 1, 1. So I'm just going to go across and put my dot there. Okay, and then I just need to make sure that there is equal distance between my dots. So I'll have another dot at -1, 3 and another dot at -2, 5, where my axis of symmetry is that x equals a half line. Okay, and then I can sketch my line in. Like so. Okay, now we haven't answered the question yet because the question has asked us to solve graphically. So to solve, what we have is that the solutions of our absolute value of 2x minus 1 equals 3 are the values of the points. Oh, it's the x values, so we might just draw a little arrow, the x values of the points of intersection. Okay, because in our equation that we're solving, the absolute value of 2x minus 1 equals 3, we only have the variable x that we can solve for. So our points of intersection are where our two graphs meet. So that's why it's really important to draw nice, accurate graphs. And that means that our solution to this is x equals -1 and 2.